All right. So the question in this case is just asking what the expected value is. Now, it's not a very fancy calculation. It's really just looking at the frequency of, so here's our joint distribution for like passenger classes to their survival. But you're really just taking a combination of like your row total times the column total and dividing this by the sample size. This is where essentially the sample size kind of plays a part to like like on the individual basis. So in this case, we're looking at our row total of values. So what is this? Row total is wow, I'm getting a little bit tired. 216 times your column total. So say if you're looking for the expected value for how many in passenger class passed away, take a look at the percentage, or you take a look at the row total times that, times the size of the column itself, which is whatever 80 plus 97 plus 368 is going to be. Then it's a simple division by the total of all values. So to a certain extent, this is where kind of having those marginal values helps. You know what I mean? So if I take my PD crosstab and calculate the Titanic values for passenger class, Titanic survived, include the margins, I can actually answer this question for myself. So 2016 plus, let's just go 545, which is the total, divided by 887, returns a value of 132 or 134. So row total, column total, if you look at your chi-square test.
Now, is there a point where we're ever going to have to index that multi-indexed crosstab, or is that, because that was a pain in the ass. I haven't looked into it.
Oh yeah, we've covered it in a couple of different ways over the last couple of classes, but absolutely, let's talk about it because there's a bunch of different ways we can do this. Yes, absolutely, it's a pain in the butt. So yeah, the expected value, it's just kind of an arbitrary breakdown of every single column, like the total, it's essentially all of the totals by their individual values. So it's not quite the average, it's essentially taking what the totals for those categories would look like if they were all essentially running similar to each other. This essentially controls for a individual value in all of those individual categories. But yeah, like if you wanted to get a specific value, let's save this to our marginal distribution. I'm going to copy paste this onto the Zoom chat so that you can follow along. That marginal distribution is now a value that I didn't actually run. So there's a couple of ways you can go about doing this. Let me zoom in here. You start by asking you want to index for let's go ahead and pick a value. Let's arbitrarily pick the value for 216. There's two ways we can go about this. Let's go over the easiest way first. If you wanted to access the column value, you start by going through the column itself. Column, in this case, is named all. You create that all column. This creates a series value that now has your passenger class as a series. That means you can.
So we would never be able to like access it through the upper level P class or age variables or.
What do you mean? Like
well, if you go back up the survived in P class, like if those I just felt like I those were untouchable, like through loc or
Oh,
iloc.
okay. So the index essentially gets transformed into, yeah, these become other. How do I access that? Well, I can come up with one method, because what this does is it creates kind of a separate index, but you can reset index,
Okay,
and then it
That's
becomes
cool.
a column value.
nice.
Yeah.
Would that be like a pivot table function? Is
It's
that
it's a pandas option to like
Yeah,
just
I like that.
restructure your pandas data frame. Mhm.
Cool. All right.
Yeah. Yeah, this is it's sort of like a pivot table. It's operating under the same principle.
Yeah, I was just trying to mess with it earlier, and I was just like hitting a wall, and I just stopped because it was. I mean, I really didn't have any like reason to, but I just wanted to get into that crosstab
Such a great
data
way to,
frame.
yeah, it's such a great way to like, such a great way to learn and break things.
Yeah,
Yeah.
in like a little sandbox.
Mm-hmm.
Cool. All right. Well, that answers my question.
Sweet. Other questions popping up, because otherwise I'll show you some Seaborn stuff. Well, Seaborn and diving deeper into how t-tests work.
I had a question from the assignment.
Yes.
I was not able to find the frequency of specific gender in a specific column,
All right.
like female in ID and in survival column, for example,
All
or
right.
male. Yeah.
Take a look at that. What task was that? Remind me.
I think it was task 3. See.
Oh, I see. Okay. So what's this doing? It wants you to create. Okay. Okay, cool. Yeah, that actually takes us back to our indexing question. It wants to do, for starters, it wants you to have your value be a frequency. And it wants you to look at so you're looking specifically for the relative frequency?
Yes.
All right. So remember, the frequency value, let's say if we're looking at sex in this case, here are male and female individuals on the Titanic. The way you get the frequency is using value counts. Yeah, value counts super easy. This is how many numbers each individual, like there's 573 males, 314 males.
Oh yeah, index it.
So you can then normalize it. And the assignment's asking you to create this to 100, multiply it by 100 to create it as a percentage. Question ends up being, how do you index that specific value? Well, you can either assign this to an object, call it survival percent, I guess, which I think is what the assignment calls it. And then that survival percent still is that same object. And you can then begin to look for it. Yeah. This is where loking, yeah. So you can look for a value from here, or you can essentially index directly. Yeah.
Thank you.
You got it. In the Zoom chat as well. What does distribution look like? I'm gonna start playing with stuff while you bring up any questions you may have. And if you have them, bring them in. But we've talked a little bit about it kind of works a little bit better. I'll honestly admit that some of these things work better in pandas in Excel. And there are some libraries that will potentially work well with Seaborn. But when you've got a chart like this, you can't really see or visualize the values fairly well. for example, you like maybe you don't want to look around. It's like, you know that 368 is the highest value, but you want to like measure based off of the short, like just want to see what the frequencies look like. Seaborn has an object called heat maps. And heat maps are really cool because I don't know if we've introduced them in class yet, but they'll take a look at a data frame object and create a set of color-based values from that distribution. You can see what this does is it creates a ranking system where the lighter colors are going to be the highest values, darker colors going to be the lowest values. You'll see that they fit in the place where these numerical values are actually included. The code for that is Seaborn SNS heat map, and then it needs a data frame to work. As part of that object, of course, you might be interested in seeing the numbers, so you can create a value where you identify the values with annotation being true. Tricky part about a note being true is that by default, it converts certain numerical properties into their scientific methods. So you do have to assign the format, which I don't remember how right off the top of my head. There it is. You essentially get to define what the format is going to be. The format, what was the value is, strong formatting when adding annotations. Off the top of my head, let's try that out. So format equals, how is it listed? What's the context for this? G. See if it works with just one. There you go. All right. So if you respond that you want the format to be at least in whole numbers, you essentially clarify that as part of the values. If you're like me and you struggle reading some of these values, you can essentially change the color map. This is what I was trying to do last week when I essentially tried a different value. I wanted kind of blue values. What I like about Seaborn is that for the most part, it'll actually return a valid name for the CMAP values. So if we run that with an accent, can't say that's much better, but you can at least see a different set of variations in your values. Helpful stuff to keep track of. Why is this helpful? Well, you can at least identify what your top values are in any given chart or any given scenario. I think some of you saw this last time. Stats. Is anyone having trouble with the t-test at this point, the one sample independent t-test? Does this make sense? Like, you understand the concept behind the distribution? Is that something you'd like me to review?
It wouldn't hurt.
Cool. Let's do this. So let's take a look at this is a different way of kind of perceiving it. Taking, actually, I'm just going to keep this. Keep the stats. So from SciPy, I'm going to import stats library. So it's all going to be part of the stats notebook. I want all of them for this particular scenario. What I'd like to do, and I'm going to stick to the Titanic data set here. So the Titanic data set, this is a series of values. Part of the premise that we kind of talk about is there a way that we can potentially determine what the value may be for all passengers crossing the Pacific or whatever, given this data set of how many rows? Let's take a look at that. 887 rows. Does this value tell us enough about, like, do we have enough values to actually make a certain assessment? So if we take a look at an average, what this is saying is that given a reference value of 29.5, given this data set of 887 values in a t-test distribution, what we might encounter is that as long as it's close to that reference value, we can expect that value or this group of the population to be part of that reference value of 29.5. Let me go ahead and just show this off. So it's t-test, one sample. This requires your values, in other words, your Titanic age, given a reference value of 29.5. As you can see, the p-value is super high, t-statistic very low, suggesting that in a distribution of, really more in a distribution where 29.5 is your normal distribution, you can expect there to be, you can expect the sample of 29.47 to be a part of that distribution. Let me quickly, let's leave that at there for now. Now, of course, if the reference value were a little bit higher, 31, that value starts to essentially fall. That value of 29.5 starts to fall off by the wayside. It's starting to be a little bit closer to the lower edge of your normal distribution and essentially starts to fall in right within that significance level. Let's try it at 30, see if that's still a close enough value. Looks about right. What does this mean? That in a distribution of numbers where 30 is your mean, or 30 is your population mean, you can expect a sample of 29.5 to still be within the cutoff point of the normal distribution values. Because what we're doing is 30 being your mean, for the population mean, 29.5 is still kind of somewhere in this area potentially. So there's still a good probability that this age, given that reference value, kind of matches up with the other values that we're working with. But in this question came up with regards to the sample size. How much does the sample size matter in this case? So let's find out. We take a sample size of random, create a bunch of random integers. If you're interested in what this is part of the random module inside NumPy. You can create a series of random integers. In this case, what I'd like to do is create a bunch of values that is really close to the mean for the Titanic age. So let's say that it's somewhere between let's actually say 29, 31. So what I'm doing here is I'm adding the lowest integer, the highest integer. So it's going to create a bunch of 29 and 31-year-olds. And how many do I want to create? Well, the size value, let's create 2,000, just to add a whole lot of values to this. So there's my array. It's all 29 and 30-year-olds in this chart. I'm going to add this to my Titanic mean. Not only that, I'm going to go ahead and create this as a series so that I can easily concatenate these values. This might not be necessary, but I'm just going to go ahead and create that as a series. So now I'm going to concat the two values. So one is the Titanic age. And the other is going to be my added two values. And we'll just type that out, call that new series. So this new series, we can expect it to have a similar mean. It's actually a little bit closer to 29.5. So it's actually the same value, which is great. So maybe this example might be in, let's see what happens with this example. Let's note that let's note the p-value here, still being at 0.26. What I want to show you is what happens when you add a bunch of new values to your series. This is interesting. Now, this is interesting because whereas in your distribution for the Titanic age, given these number of samples, you still had a probability that your reference value was going to be somewhere within that distribution. But the second you included over 2,000 values, something happened to the distribution of your series that meant that this p-value, that this population mean, is less likely to be part of the distribution given your, like, if your null hypothesis were to be true. What does this look like? Or what do I mean when I refer to what this looks like? Remember, this is the original distribution of the type, whoops. That's the age. When we look at the distribution of the Titanic, we see that it's got a fairly normal, it's got a bit of a right skewed distribution, even though it's unimodal, essentially reaches out to a certain distance. That population mean of 30 could be expected to fall potentially somewhere around here, suggesting that there's a very high probability that this population still exists as part of the distribution. But the second you include new values or a lot of new values, you'll note that the distribution essentially peaks. And because you have so many values, your mode gets so much higher. Your mean and your median essentially all increase in frequency. That means that the distribution of your bell curve essentially became quite narrow. Stop typing there. And it means that there's a lot more space, or a lot less space to throw underneath your 0.05 significance level. Now, this is obviously not to scale. As a matter of fact, like based off of what we're seeing from our p-value, we can assume that the location for the number 30 is going to be very small. In other words, what this distribution suggests is that when you consider the number of values being accounted for, 30 may not necessarily be the specific population. Now, remember, we just created a bunch of random values. We created 2,029 and 30-year-olds that we added to the data. So that is a device given this data set. If we wanted to convert this a little bit, say if we wanted to add a little bit more variety to the age range, say 25 to 36, we can expect a little bit of a wider distribution, and your p-value still falls into place. So why am I mentioning this? Well, specifically because it's all about the averages in this scenario that we're calculating, that we're essentially looking at the frequencies of these different sets of values. So what the t-distribution allows us to account for is where does a population reference value, or where does a population mean, fall within the distribution that we're working with. Not sure if that helps in any way, but if I can explain it in another way, let me know. So the question is, if you're working with skewed data, like what, or at least when you're working with skewed data, So I'm going to make a couple of assumptions. One, we're working with skewed data, and the assumption is that we're looking to run a t-distribution test. If we are intending to run a t-distribution test, what I know about the t-distribution is that it follows very similar patterns to a normal distribution. It's just a little bit more flexible when working with smaller samples. Thanks to the central limit theorem, we can posit that any like taking enough samples off of any distribution will return a normal distribution. The t-distribution or the t-test essentially follow very similar ideas, where if you take enough values from any type of distribution, you'll see that value being normalized. So when you're running a t-test, it essentially runs on the, to keep it simple, when you're running the t-test, it's running on the premise that any distribution can be converted over to a normal distribution, and then you can essentially run the t-tests on with those values. Let me see if there's a good way that I can visualize that. So let's go ahead and just take this Chi2, because this one is skewed. Age. Let's go ahead and take a bunch of samples from here. So Titanic age sample. Does it have a replace value? Come on, dot sample. Sample pandas. I just need the documentation because it's not popping up. Replace, true. Not replace. No, we don't need to replace it. Okay, so we're taking 40 random samples from a sample of distributions. Let's take this list of samples. That's simple. Samples. I'm going to make this an empty list. And what I'm going to do is for I in range, let's say 100 times, list of samples appends. And this sample value. No, we're taking the sample, we're taking the average, we're taking a bunch of averages from all of these samples. So we take all of these samples and we're going to create a list of sample means. Sample list of samples, let's take a look at that. So that's all of the averages. We took 100 averages. As a matter of fact, let's keep it closer to the t-distribution. Let's take 10 of those samples. Let me go ahead and reiterate what I did here. We're taking samples, so essentially 40 individual rows, calculating the means and adding that to a list of values. When you take all of those values, say you start with 10, you can actually plot a histogram from that value. Let's try this as the SNS.histogram, histplot, turn that as a list of samples. See that the count isn't pretty big yet, but as you increase that number, you can start to see that there's a little bit of a change in the distribution. And as you increase that more, say that to 1,000, by default, a list of samples are averages. This is from the same non-normal, like the right skewed distribution. The central limit theorem returns a very normal distribution. So the good news is you don't really have to worry about if your distribution is skewed or not when working with a t-distribution, because the t-distribution is essentially accounting for this pattern when it's calculating whether to reject or fail to reject the null hypothesis. The thing you have to look out for is ensuring that you have enough values in your data set in order to account for this properly.
Thank you so much. This is really new to me and very helpful.
Yeah.
Making random samples out of a data set.
Yeah, let me send this your way.
Yeah.
I'm sending this on the Zoom chat, so you've got a copy of it.
Awesome. Thank you.
Yeah, and it's in the notebook too, so you can take it back.
So basically, the computer or Python, from our sample, it randomly reproduce this sample to thousands and then pick randomly from those thousands for one random sample here.
So what I did, so take this step by step. Yeah, so essentially what I did is if you look at your Titanic, this a sample actually works with any type of tool. So for example, say I wanted to grab a random sample from the Titanic data frame, you can click sample 1 and it brings you a random sample or a random row. Same principle applies with a series value. So you take age and a series value. This is row 158. So note that that's row 158. So you can use Titanic iloc to locate row 158, and this will return the person who's 5 years old on the Titanic, did not, oof, that is tragic. Third class passenger was 5 years old, did not survive the Titanic sinking. They only named their father. Random. Okay, so you take a look at that value. And what we do is I take 40 of those samples and I calculate the mean of those samples. So if we take, for example, the same part of the function, return it down below. Got 40 of these same rows. I calculate that mean. That mean for these values is 29.6. But that mean then gets added to a list of samples 1,000 times. So it's all different sets of combinations. And that list of samples, so yeah, so that's where we get this normal distribution.
Wow, it's amazing.
Yeah, this is the part where statistics gets fun, because it is counterintuitive. That's like, but like your distribution is totally skewed. How are you not getting? And I was just like, let's play math. You just run a bunch of averages multiple times. I think in the class, in the recording yesterday, I kind of showed this with the binomial distribution as well. Let me just make sure if that's in the recording. No, this was yesterday's. Well, let's go ahead and just show it off. So NP, now that is stats. I know. Yes. No, that's not what I'm looking for. How do I create a bunch of binomial distributions ready to go? Go ahead, creating binomial pandas, because I cannot remember off the top of my head. Binomial distribution. Blah 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 blah. Oh, okay, it is binomial stats. That part makes sense. Nope, no. Stats binomial. Let's do 10. P, how many? So 1 or 0, and then let's do 10. Just list it. I'm guessing Steven's probably almost done with their version of creating a binomial distribution. Python. Random binomial. That's what I was looking for. All right, random binomial. All right, so random binomial. What do we need for this? That's from NumPy random. binomial. There we are. So number of times that you want a binomial distribution. Let's make 10 of these. Let's make 100 of these. What was the other one I missed? Number of trials, probability of each trial. Okay, perfect. So number of trials, probability of each trial. Let's see. Here we go. 56. How did I do this with the other notebook? Let me just quickly, let's go back to that. What I want is a list of those values, not the, it's not that I want, it's not that I want the individual answer. The size. All right. Whoops. That's what I was forgetting. All right. So I've got values between 1. Let's create 100 of these. I'm glad I forgot this. So let's create 100 of these. So now cool. We now have a bunch of 1s and 0s. You take this to be your values you want to calculate. And if you take that histogram, or that hist plot, let's clean this up a little bit. Great. So we've either got a 1 or a 0. Now, if we end up doing the same thing that we just did above with this distribution, we'll see the exact same thing happening where take the list of samples, just going to go ahead and copy paste all of it, bring it back down. Just rename it to the proper values. So append values, let's take 40 of each particular situation, calculate that mean, and then essentially run the same distribution. Fine, I will convert this into a pandas. Fine. There you are. This one's even more interesting because in this case, any situation where you're looking at a 0.5 degree percentage is going to like go in one direction or another. If you skew this a little bit, this is where things get interesting. Still essentially return, like it skews your distribution a little bit, but even still it seems to value something a little bit more. So we're still returning fairly small set of values with 1,000. What happens if we increase the number? One, it takes a little bit longer to run, but even then your distribution becomes even more normalized. So it doesn't, again, because what we're calculating is the average values of these two numbers. So we're essentially trying to calculate 0.5 or 0.3 consistently from any type of distribution. Other questions? this because, yeah, so the question, this is a question we normally get where it's, what's the difference between 0.975 and 0.95? Well, this is where understanding what kind of distribution you're working with sort of falls into place. Because when you're looking at most distributions, or the types of distributions that we're working with in this class for the most part, for a t-test, you're working with what's called a two-tailed distribution. So called this section of your distribution and the other section of your distribution tails. So that means that you have two places to which to set your significance level. Remember, we established a significance level of 0.05 by default. With a two-tailed distribution, that means that your 0.05 needs to be split between both sets of values. So that means 0.025 in one corner versus 0.025 in the other. So for your PPF, as part of your calculation, because you're working with a two-tailed distribution, you specify that you want a confidence level of 0.975, specifically because you're dividing this between two sections. Now, here's the tricky part. Some tests and some types of distributions are one-tailed distributions. So, say, for example, if we have our graph, that's our X or Y axis, you could very well end up having a distribution that kind of looks like this, or potentially looks like this. For whatever reason, might look like that. Probably unlikely. This is more like a sine graph. So, but the point is, this isn't a two-tailed distribution. This is only one-tailed. And for that, your 0.05 for your significance level tends to fall somewhere in this area. Or like that's your cutoff point. So the idea is whether you split your cutoff point in half when you're working with a one-tailed versus a two-tailed distribution. Okay. With that said, folks, if you have no other questions, I'm happy to chat with you later. I have a couple of things I need to go ahead.
Julian,
Yes,
one more
sir.
question, please. I have problem in switching between like from series to list or list to series. If
For sure.
you a little bit explain that.
Yeah. So, okay. So no.
Sometimes I get better. It's not a list or a series.
Yeah. And this is where it's important to sort of recognize your data types, because we created, what was it, list of values, list of samples. A list of samples on its own, I don't remember what I created it last time, essentially returns a list value. When in doubt, note that these, for the most part, have very similar attributes or will behave the same way. Whoops. For example, here a list of samples is a list and that means that you can index through your values normally, right?
Yes.
So say that we were going to try to recreate this. Let's create a pandas series object where I take my list of samples and convert it over to a series. This returns a pandas series. However, and the way you identify or the way you convert that, I'm simply using PD series to serve it as a, like specify like, hey, this is a type of value. This is a data type. But because this is a pandas series, the list options still work, they still run the same way. You can index through these values exactly the same way. The same goes for if you tried to change this over to a NumPy array. I promise I'm getting somewhere with this.
Yeah.
Works the same way. The problem really ends up being for when you take your list of samples and you try to use some of the functions that we've been using at any given point. So for example, list of samples has append and all that. Let's say I wanted to find the, the mean of these values like I would in pandas. I can't do that because a list object has no attribute for mean. But a pandas series, because it's a pandas data type, does have an option for mean. And let's find out if NumPys have it. It does. But even no, sort of returns a different value. So different, yeah.
Thank you. That helped a lot. Yeah.
Absolutely. So just note that it's going to get tricky, but if you need to change it, you can always just convert them for the reason you may need to convert them.
All right. Thank you so much.
I have a question. It's more general.
Mm-hmm.
I've been having trouble these last 2 days drinking from the fire hose, as we say. Like it's been lots of overwhelm. But what you were saying about going into detail about the equations next Thursday gives me a little hope that things might be slowing down. Is that?
So
that smile frightens me.
No, it's okay. So tomorrow, okay. So here's what's interesting. Tomorrow we go into a topic that we never discuss again as part of Unit 1. It's very, like, it kind of seems to come out of nowhere, but it's really important within the framework of some of the functions you're going to be using or some of the models that you're going to be building down the road. How should I put this? The state that we're currently in is, come Thursday, I'm going to show you the first predictive model you'll be able to build. But that model is like a Lego set that already has some of the big parts already put together. And it's just like, put this one on top of this one on top of that one. And like, you see how that works. But what you're seeing here, like yesterday and today, is all of the small Lego pieces essentially scattered on the floor.
A minefield.
Correct.
You dads can tell you.
Yeah. And so like the idea is between learning to code last week and understand the simple statistics that you're going to need to know to make the models work, things on generally starting Thursday. So starting tomorrow, we go into Bayes' theorem. I talk a little bit about history. I make a slightly weird example, kind of comes out of nowhere, to talk about how Bayes iterates through values. And then it's important to note that you need to know that Bayes iterates through its own values in order to fit into a specific model, like what the model is doing, what some of these TensorFlow models, some of these machine learning values do is that it takes information that it's just learned, reapplies it back to its own formula.
Cool.
And knowing that is part of why we teach Bayes and never discuss it again. What we're talking about right now comes back again on Thursday, because we use these same types of correlations or these same type of principles to address the correlation between individual features. Then we essentially talk about it at length on Tuesday and Wednesday. On Monday and Tuesday of next week. On Wednesday, we do a little bit of linear algebra, which is essentially the last 2 days where we just spend all this time looking at equations and how they work.
Okay.
So, yeah.
No, thank you for breaking that down. That it sounds much more palatable when you put it that way.
Right.
Like we're building a Lego Death Star, but we need to make the Lego spaceport first.
Correct. So, yeah, like I'm not gonna lie, this like I recognize the overwhelming sense of it, particularly because this isn't something you've seen in a long time. Like for one, I really appreciate, Stephen, that you're sharing a lot of additional resources, because that is like that's going to be super helpful, because other people explain things differently, and that is excellent. So keep that up. The things that we look at today come back again, or essentially fit into the picture starting week 5 and 6. So week 5 and 6, you start seeing like, oh, that's where this comes from, or oh, that's why this is necessary. Yeah.
Okay, cool. Thank you.
Yeah, thank you. I will let you all go then. In the meantime, unless other questions.
All right. Thank you, Julian.
Thank you, folks. Talk to you all very soon. Share and conversation.